Space Eagle is at tranquility, over.
Hi, I'm Blair Thompson. I really enjoy orbital mechanics, and it's been my privilege and honor to work in the U.S. space program in different capacities over the last 20 or so years, both on the civilian side and the military side. I'm proud to say that a couple of my algorithms have flown on both manned and unmanned spacecraft flying up to the International Space Station. And my algorithms keep the spacecraft from going into the wrong orbit and actually running into the space station. It helps keep the astronauts safe and the space station itself. Today we're just going to be talking about the very fundamental level of orbital mechanics. What keeps things in orbit, what keeps them from falling out of orbit and hitting the Earth, and what determines the size and shapes of orbits. And then finally, what are the different orbits useful for? I wouldn't be where I am today without knowing those basic fundamentals, and that's where it all starts. All objects in space, including active satellites, debris, space junk, and planets and moons, all of those objects are moving along a trajectory or a path that we call an orbit. Usually a smaller object like a satellite orbits around a bigger object like a planet or a moon, and it's the gravity of that bigger object that keeps the small object in orbit around it. Without gravity, the smaller object, the satellite, would fly off into space to never return. The idea of an object orbiting around the Earth is very similar to a race car going around the track. The race car must keep moving in constant motion round and around the track. Let's start by considering what an orbit is, what keeps a satellite in its orbit, and what keeps the satellite from falling out of orbit and hitting the Earth. Let's look at the problem through the eyes of one of the original orbit geniuses, Sir Isaac Newton. As we do this, keep in mind that back in Newton's day, the idea of objects going around the Earth, or the Earth orbiting around the sun, that was some crazy stuff. People who thought like that were either lunatics or heretics. Fortunately, Newton stood on the shoulders of giants, and in 1687 he published his famous work Principia. You know that whole shoulders of giants, that's like his quote. In Principia, Newton proposed a simple thought experiment, a cannon on top of a large mountain. In this case, the cannonball will be our satellite. So we know that an orbit is the path that a satellite follows around the Earth, and in this case it'll be the cannonball in the orbit. But what keeps that satellite in its orbit, and what keeps it from falling out of the orbit and hitting the Earth? Check out the following video, which does a great job illustrating the concepts behind Newton's cannon.
So how does orbiting work? Let's take a page from Isaac Newton. He had this idea, a little mental experiment. You take a cannon, you put it on top of a hill. If you shoot the cannonball, it goes a little bit ways. But if you shoot it harder, it goes far enough so that it lands a little bit past the curvature of the Earth. Well, you can imagine if you shot it really, really, really hard, it would go all the way around the Earth and come back, boom, and like hit him in the backside or something, all right? Let's zoom way back and put you in a little satellite over the North Pole of the Earth and consider north to be up. You're going to fall down and hit the Earth, but you are actually moving sideways really fast. So when you fall down, you're going to miss. You're going to end up on the side of the Earth, falling down, and now the Earth is pulling you back in sideways. All right, and so it's pulling you back in, and you fall down, and so you miss the Earth again, and now you're under the Earth, and the Earth is going to pull you up, but you're moving sideways still. So you're going to miss the Earth again, and now you're on the other side of the Earth, moving upward, and the Earth's pulling you sideways. All right, so you are going to fall sideways, but you're going to be moving up, and so you'll miss, and now you're back on top of the Earth again, over the North Pole, going sideways and falling down.
So in Newton's cannon demo, we have a cannon on top of a hilltop, firing cannonballs horizontally. And as we increase the speed, the velocity at which those cannonballs leave the cannon, that changes the size and the shape of our orbit. And if the cannonball is going fast enough, it'll come all the way around the Earth and hit the backside of the cannon. So can we make the cannonball go even faster? Sure. Put more powder in the cannon and the satellite will go faster, the cannonball will go faster, and we'll actually go beyond that parabolic orbit into what we call a hyperbolic orbit. And that's the type of orbit that organizations like NASA will use to fly out to explore the other planets. So we see that it's the speed of the satellite that determines the size and the shape of the orbit that it's in. But it's important to remember that whatever speed we launch the satellite with, or that we fire the cannon with, that object, the satellite, will always come back to that original point, and it'll just follow that path over and over, and that's the orbit that it's in. Before Newton came along, there was a lot of people that spent a lot of time thinking about orbits and objects moving through space. And one of these guys was Johannes Kepler. So Kepler gave us the shape and some of the other properties of orbits, but, fun fact here, what he tried to relate orbital motion to was cosmic musical harmonies. He thought that's what was keeping planets into orbit and driving them along their paths. Then Newton came along and he gave us the idea of gravity, and that's what's driving the satellites in their orbits. What Kepler did get right was his 3 laws of motion. Let's review those. Kepler's first law tells us that all orbits are elliptical in shape, and the Earth is not at the exact center of the ellipse, it's off to the side at one of the points we call the focus point. So some of the properties of ellipses are that they are flat, two-dimensional, they don't move through space like a horse saddle or a Pringles potato chip. They're flat, they're two-dimensional, planar. And orbits, ellipses, close back on themselves. They follow the same path over and over and over. And so that's what an orbit does. A satellite in orbit follows the same path around and around. Kepler's second law, now because the Earth is not at the center of the ellipse, as the satellite moves around its orbit, the distance between the Earth and the satellite is going to be constantly changing. And there's going to be one point on the orbit that's closest to the Earth, and that's what we call perigee. And there's another point that's going to be farthest away from the Earth, and we call that apogee. It's a lot like a roller coaster here on the Earth. You're going fastest at the lowest parts of the track, when you're closest to the Earth. That's where the roller coaster is going the fastest. And the roller coaster is going the slowest when it gets to those peaks, those high points on the track. That's similar to perigee and apogee and the speed at those different points. Now, Kepler's third law tells us that there's a relationship between how big the orbit is and how long it takes to go around one time. That amount of time it takes to go around, we call that the orbital period. And it kind of makes sense, but Kepler's third law tells us that the bigger the orbit is, the longer the period is, the greater amount of time it takes to go around one time. So now that we've looked at some of the basic properties of orbits in general, let's take a closer look at some of the categories that we put orbits into and what each of those different types of orbits are good for. We typically categorize orbits by their size, their altitude at which the satellites are flying around. So we have low Earth orbit, medium Earth orbit, and then we have a special type of orbit that's the highest type of orbit, and we call that a geostationary, or geo type orbit. And then there is a special category that we give to orbits that are very elliptical, very stretched out. We call those highly elliptical orbits. So let's look at each one of those orbits in a little more detail. Okay, so first let's talk about low Earth orbit, or LEO, L-E-O. There's no real hard boundary set for where LEO begins and ends, but typically it's around 200 miles or so. To give you a point of reference, the space station, the International Space Station, is about 250 miles above the surface of the Earth. And to put that in a little context, that's about the distance from New York City to Washington, D.C. So not really far away, right? We think of being out in orbit as being in deep space or outer space, but it's really not all that far away when you're in low Earth orbit. An object in LEO, a satellite, is typically going about 17,000 miles per hour, or 7.5 or 8 kilometers per second. So it takes a lot of fuel to put objects up into orbit, and that's why we have these really big rockets that launch off the Earth and put relatively small satellites up in orbit. Okay, so we're going really fast. What about that speed relative to objects on the surface of the Earth? We're down pretty close, it turns out, right? 250 miles or so. Going really quickly over the surface of the Earth, we don't get a whole lot of what we call dwell time. In other words, the satellite in LEO is flying over the surface of the Earth very quickly. And typically to go from one horizon to the other, for someone standing on the Earth watching a LEO satellite fly overhead, that's a pass of about like 8 or 10 minutes or so. That's how quickly a LEO satellite will fly from one horizon to the other horizon for someone standing on the surface of the Earth. So typical missions from LEO would be like weather or other Earth observing missions, science, that sort of thing. And then, except for the Apollo astronauts going to the moon 50 years ago,
One small step for man.
all of human spaceflight is done in LEO. So the International Space Station, again, is in a LEO orbit. So going further out away from the Earth, we come to medium Earth orbits, or MEO, M-E-O. And again, there's no hard minimum or maximum altitude range. This is the altitude at which there's a special type of orbit called a semi-synchronous orbit. In other words, it makes 2 orbits per day. And that happens at about 20,000 kilometers away from the surface of the Earth, which is about 1.5 Earth diameters away. This is the altitude where the GPS, the Global Positioning System, navigation satellites work and operate at 20,000 kilometers in that semi-synchronous Earth orbit, meaning 2 orbits per day, twice around the Earth every day. At that altitude, there's nothing really magical about that in terms of navigation. It's just a convenient place where you get a good coverage of the Earth from a few satellites up in space at that altitude. Now, if we go out even further away from the surface of the Earth, we reach a special altitude where the GEO, or geosynchronous, geostationary satellites operate. And at this magic altitude, which is about 35,000 kilometers away from the surface, the orbital period of the satellite matches the rotation period of the Earth. In other words, about 1 orbit per day. A satellite in a GEO orbit appears to be stationary from someone standing on the surface of the Earth looking up at that satellite. So that satellite appears to hang over the same point on the Earth's equator all the time, 24 hours a day, day after day. That type of orbit is really good for weather, again, looking down, getting the big picture of weather, but also communications. And especially like, satellite TV, where you don't want to have to keep moving your antenna all over the place. Once you plop down that satellite dish and aim it up at that satellite, pretty much you don't need to move the antenna again because it's in that geostationary orbit. And again, that occurs at roughly 35,000 kilometers. It's about 3 Earth diameters between the surface of the Earth and the geostationary orbit. So LEO, MEO, and GEO are categories of satellite orbits based on their altitude with respect to the Earth. So there's one more category that we put satellites in, and that's called a HEO, highly elliptical orbit. And with a HEO, you're actually passing through different levels of altitude, so it doesn't really fit nicely into one of those other categories. And really, a HEO can be any altitude really above the surface of the Earth. The property there is that the orbit is really elliptical. It's really been stretched out. And that altitude could actually go anywhere from LEO all the way out to GEO or beyond. And a good example of a HEO orbit is the old Soviet Union Molniya orbit, which was a communications type satellite that was in this highly elliptical orbit. The reason they liked that type of orbit was because when that satellite was all the way out at apogee, it would spend most of its time over the northern hemisphere and be useful for communications in the northern hemisphere. Let's go over what we've learned so far. So it's the gravity of the Earth that keeps the satellites in orbit. But why don't the satellites fall down and hit the Earth, fall out of orbit and hit the Earth? It's the speed of the satellites kind of balancing out the force of gravity. Remember Newton's cannon? We had that cannon ball going at a certain speed. It was falling towards the Earth, but it was going sideways fast enough that it actually stayed up in orbit. And that's how all orbits work. And so then we have this big, huge family of orbits. We broke those down by altitude, LEO, MEO, and GEO. And there was different advantages to each different type of orbit. And then we also had that special kind of orbit by itself based on its shape, the highly elliptical orbit, the HEO. So with these fundamental building blocks of orbital mechanics, you can take this knowledge and build a spacecraft and fly it in any one of these types of orbits. And it always comes back to the gravity and the speed, that fundamental properties of physics that keep the satellites up in orbit. And I hope that you can take these same fundamental principles and do something really creative and something really innovative in your Space Force career.